And like I have trouble with Keith and Kevin. I know that sounds funny to you guys, but they start with the same first 3 letters, and it just freaks my brain out. Isn't that weird? I think I'm like ADHD, and they didn't have those words when I was a kid. So anyway, my kids are sure of it. They say, Mom, you're like all over the place. Oh, sorry. Anyway, and so I had trouble distinguishing things and keeping them straight, and so I have little tricks to help me. And these 2 words are very similar to me. So I wanted a way of remembering which one was which. The longer word is the one that's doing the dissolving. The shorter word is the one that's being dissolved. So if you're putting sugar in tea, which one's the tea? Solvent, right? Because there's more of it. It's a longer word. Which one is the sugar? Solute. It's being dissolved. It's the shorter word. There's less of it. That's how I remember it. You guys remember it any way you'd like. Okay? But that's how I remember it. And then when you do have something, so this is the dissolver and this is the dissolvee. How's that? But when you do have these and something is able to be dissolved, then you end up with a solution. Now, we get an experiment here. And the experiment is experiment 5.1, and it's called diffusion. And we have changed this a little to make it more practical than you tasting something here as a group together. And I put a tea bag into a cup on your table. I don't know why he didn't have them do a tea bag with this, because it's so much easier. Because there's your diffusion. This started as clean water that I poured in here. Is it clean water anymore? No, it's got tea in it, doesn't it? And that's the whole premise of tea. Diffusion is absolutely essential to making tea, okay? And so, what is diffusion? Well, on the top of page 135, it defines if diffusion is the random motion of molecules from an area of high concentration to an area of low concentration. Now, I don't know about you, but memorizing all these things on a test, I would just go out of my mind and really freak out. So, I'm going to try to make this a little easier for you. Turn the page for a minute. Bottom of the next page. It's got osmosis. And it says the tendency is of a solvent to travel across a semi-permeable membrane into areas of higher solute concentration. Huh? Okay. I'll tell you what got me through college with these. Water moves from more pure to less pure. Write that down. Water moves more pure to less pure. I had to come up with something to help me to be able to answer these kind of questions. Water moves from more pure to less pure. Living systems, water's usually the solvent. And there's other things that are dissolved in the water, right? The difference between osmosis and diffusion. Diffusion, my glasses are stuck. Come out of there. Okay. Diffusion, add the word random. Diffusion is the random motion of water going from more pure to less pure. Osmosis is this process across the semi-permeable membrane. I know, we've got to define that. It's all good. It was the vocabulary word right above the word osmosis. So we'll get back to that. I want to show you the similarity and the difference so that you can grab a hold of it. Now, first off, can you remember water moves from more pure to less pure? Sure. All you got to do is think of your bedroom. It moves from more pure to less pure, right? Things move that way, don't they? Our lives move from more pure to less pure, unless it's for Jesus and he brings us back, okay? But things go to a mess if left on their own, don't they? Yeah. So water moves from more pure to less pure. No big surprise. Random motion is diffusion. I had a tea bag. I poured water into it that was clean water. It couldn't leave it at that, though. The molecules dancing around went from more pure, which was the clean, into the tea bag, which is where it was less pure. And they kept going in and out, doing that until all of it was the same, less pure. Does that make sense? So that random motion will continue until all of it has the same concentration. It will equally be less pure. How we doing so far? You see how it's random. It's just bouncing around in and out until it accomplishes that. Okay. And on the bottom, right below, on the top of page 135, right below diffusion, it tells you concentration is how much solute exists in a certain amount of solvent. And you're kind of aware with concentration, aren't you? You know, like if you get that lemonade or the orange juice that's in the can and you dump it into a pitcher and then you dilute it by putting 3 more cans full of water in it. You guys done that before at some point? Try eating the lemonade out of the can sometime. I like sour, and with the sugar rush, though, will kill you, so don't do it. Anyway, and so a concentration tells you about how much is dissolved in a solvent. That's what it's telling you. And they're trying to help you with the definition that they've given you there, but I think this one's a little better. So diffusion is random motion of water moving from more pure to less pure. Now, if you're using something other than water, it's still kind of working the same way. Because what happens is things will continue to move until everything is equally polluted or distributed, however you want to look at it. Okay? That's diffusion. Osmosis is the same process, but going across a semi-permeable membrane. So turn over to page 136. Now, I want to break this word down with you. Semi. What's a semicircle? Half a circle. So semi means part of something, right? Usually half. But let's think part of something. Permeable. If something is permeable, what does that tell you about that something?
Things can go through it.
Thank you. Things can go through it. Semi-permeable means some things can go through it, but not everything. That wasn't hard, was it? I mean, it sounds like a mouthful when you go semi-permeable membrane. It's easy. It's kind of like supercalifragilisticexpialidocious. You know what I'm saying? It sounds like woohoo, but it's not. So semi-permeable and a membrane you can think of like a skin. It's really like a skin. So a semi-permeable membrane is actually something that lets some things through, but not just everything can go through. That's what it is. Now let's apply that back to where we were with osmosis. We said that when water moves from more pure to less pure across a semi-permeable membrane, now it's not random anymore, is it? It's not random anymore. It's going in one direction. And it's because of the semi-permeable membrane. And it will continue to go across that membrane until it's all equally polluted, just like before. Yes, just like before. And actually, the picture on the bottom of page 137 is trying to show that to us. So, and you know what, I won't do it exactly what they did, but here. If you start off and you have a whole bunch of solute over here and a little bit of solute over here, and then in the next picture, it shows that it's all equally polluted, okay, and the water level hasn't changed. And then on to the right of that, in your book, you have this next one is more solute over here, less solute over here. Once again, only this time, this time we ended up with this, and then all of them are equally polluted. Now, if you're looking at those two possibilities, which one is random motion until everything is equally polluted?
Diffusion.
Right. This one is diffusion, isn't it? Because it's random. It just keeps moving around until everything is basically the same. This one, the water moved from more pure to less pure and got stuck because of the semi-permeable membrane. And it did it, though, until all of it was equally the same concentration. The solute is equally polluted into everything. But the water gets stuck in one place because it's going across the semi-permeable membrane. See the difference? Does everybody see there's an actual direction that it's going in, and then it gets stuck there because of the semi-permeable membrane? That's osmosis. Diffusion, it can go both ways. Now, the experiment that they had for that one was actually quite fun. And hopefully some of you did that. I know Ryan did, and thank you for that. How I finally worked out, I used to just, it's several days, how can I do this for you? And then I figured out if I took 2 eggs that were the same size, and I put them both in vinegar, and then a day later I put one in vinegar, and a day later I put one in distilled water and one in Karo syrup, then I could show this to you. And hopefully everybody did this, because this was kind of a fun experiment, wasn't it? Yeah, it really was. Now, these were done, and I'm going to let you tell me. This is going to be nasty. I'm going to have to, as a matter of fact, when I get done with this, can you just, do I have any wipies? Hang on. Because I know what my hand's going to look like after this. Yeah, this should work. I should be okay. Okay, let's do this one first. What's a dead giveaway of what that one's in? But look how small the egg is, and look how dehydrated. Do you see how dehydrated the egg is? It's absolutely dehydrated. If somebody just asked, where's the shell, you didn't read the experiment. And you were supposed to read the experiment. Remember, you were supposed to put this in vinegar first, and the vinegar ate the shell away. That was a chemical change because it ate it away, okay? And then you were supposed to put your egg into Karo syrup, and this is what the egg, it shrinks in the Karo syrup. And then you're supposed to put the egg in, I'm not sure which order this was supposed to be in. You're supposed to put your egg in distilled water. I didn't even use distilled water because I didn't want to have to carry it on my bike. And my car was broken down this week, so I just used regular drinking water. But look at the difference. These eggs started the same size. Okay? Those eggs started the same size, the exact same size. I actually went to great lengths to make sure I started with 2 eggs that were the exact same size. I went through 24 eggs to find 2 eggs that were exactly the same size. I'm serious. I wanted to really give you a fair look at the difference. Okay? Now, this one was in distilled water. This one was in Karo syrup. And I'm putting these back in here now. You see it bounce? Wow. Okay. Hang on. Let me just wipe my little paw. Oh my goodness. Now I'm going to smell like Clorox. What did we see here? Wow. When we put the egg in syrup, and then we have the egg over here. I know it's a circular egg, don't go there. And this was supposed to be in distilled water. The D stands for distilled, okay? Which way is water going to move? More pure to less pure. Everybody say it. Water moves from more pure to less pure. Got to memorize that part. Okay. So, where is it? And remember, in living systems, they all have semi-permeable membranes because that's the membrane that we call skin. It's the membrane that we call plasma membrane that's around the outside of the cell. We're full of semi-permeable membranes. This is why a lot of the medicines that they do now, they use patches to put on you, and then you absorb it through your skin. This is why those of us that use them use essential oils, because we can absorb them through our skin. Okay? And so these are semi-permeable membranes. Okay? So there's a semi-permeable membrane on this egg. There's a certain amount of solutes in the egg because the egg has in it little parts. You've already learned in the bacteria how it has DNA, and it has cytoplasm, and it has ribosomes and things like that. There's stuff in the egg, right? Okay. Where's the water more pure when it comes to the syrup? In the egg or in the syrup? Where's the water more pure? In the egg. It's actually more pure in the egg because the solids in the syrup, that's why the syrup just pours like syrup. That was good. Okay, so the water moving from more pure, I'm going to put my pen on more pure, and I'm going to put my arrows to less pure. This is how the water's going to move. It's going across the semi-permeable membrane. So what did the egg do? The egg shriveled up, didn't it? It shriveled up. And that's what we saw, a little shriveled egg. Now I'm not grabbing it again because it's gross. But you saw it. It's a little shriveled up egg. And here in the water, even with drinking water, where is it more pure? Outside in the water or in the egg? Where's more pure now? Outside. Very good. So now I'm going to put my pen where it's more pure, and I'm going to point it to where it's less pure. Now the water is moving into the egg, and what did we get? A big old bouncy egg that actually bounced when I dropped it into the jar again, didn't it? Huge, right? And that's what yours ended up with, because you ended with water. It's huge. It got very swollen. Why? Because the water moved into the egg but can't move back out of the egg because of the semi-permeable membrane. Let's apply this to a past chapter. When we studied Kingdom Protista, and we studied about the protozoa, we remember that they had a contractile vacuole. The contractile vacuole squeezed out excess water, didn't it? Now you know why. Because that poor little protozoan, as it's swimming around in the water is more pure than the protozoan's cell. Because it's got, its gullet and its vacuoles and all the parts in there. So the more pure is outside, the less pure is inside. What's going to happen? This little dude's going to blow up and explode. Okay? Because of osmosis. So what did God design? He put in there contractile vacuoles, little pumps, squeeze, 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 for it to pump the water back out so the little guy doesn't explode. Does this make sense now? And now you know why. Because of osmosis. So far, so good? Okay. Let's kill all the syrup pictures. Otherwise, you guys will be running out of here wanting pancakes. Okay. I'm going to give you a real practical application. You ever had lettuce that was wilty? You get the lettuce out and it's wilty. What does your mom do? If she doesn't throw it out, what does mom do? She sticks it in a bowl of cold water. You know why? That fresh water will osmose back into the cells, and it'll give it what's called turgor pressure again, which you're going to learn about in the future, and that makes the lettuce come back. Because the water moves from more pure to less pure, goes back into the cells, and it makes the lettuce okay again. Yeah. Obviously, you don't eat a lot of romaine lettuce. No. Okay. I don't eat iceberg, but with romaine, with real greens, real leaves, you can put them back in water, and that'll go right back in, and then they'll be crunchy again, and you can eat it. So, anyway, practical application. Can't tell I'm a homeschool mom. Okay. So, on page 138, it tells you that this is why if you're in a ship and you run out of water, you can't drink the salt water. Think about it. What would happen if you drink the salt water? It would literally suck the water out of your cells. Think about it. You drink salt water. Here's you, there's your stomach, okay? You drink salt water. The salt water is a really high salt content compared to your cells. What's going to happen? The water's going to move from your cells into the salt water. It's literally, as you're drinking the water, you're going to dehydrate further because it's literally going to be sucking the water right out of your cells and kill you. Does that make sense? Osmosis is a very practical thing to know about because it really applies to real life stuff. So it's very practical. And that's why it tells you here on page 138, water everywhere, and all the boards did shrink. Water everywhere, nor any drop to drink. I had a dog once. I still have lots of dogs, and I still have bird dogs, but I had a bird dog once that I used to take to the beach up near Ormond Beach, and it was a place called Crescent Beach, which was great. That was back when you could take dogs to the beach. And my dog was chasing after the birds because she was a bird dog. Didn't know it was a bird sanctuary, but that's another story. And she was having a ball. And she got hot and tired, and we had water at the truck, but she started drinking the salt water. That dog got so sick. And I couldn't get her to stop fast enough, and she got so sick. Now, she did survive, but she got very sick. So it's not ever a good idea to let them. And watch your dogs, because they don't know any better. They will drink that salt water. They'll go, well, it's water. You know, it's like, no, 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 no. You don't want them to do that. Okay. So, bottom of page 138. A semi-permeable membrane is placed in a beaker. Equal amounts of salt water solution are placed on each side of the membrane. But the solution on one side is twice as concentrated with salt as the solution on the other side. After 1 hour, the water level of the solution on the right increases and the water level of the solution on the left decreases. Which solution started out with the higher salt concentration? Okay, because the water moved to the right side from the left side, so the right side had the higher salt concentration because it moved from more pure to less pure. Guys, you're going to be applying this as we go along, and I'm going to build a whole bunch of other vocabulary words off of what I'm teaching you today, okay? Because you're going to learn about plasmolysis, cytolysis, and if you had to just memorize all these things, but I'm going to walk you through the word roots. And if you'll memorize the basics that I'm telling you and then the word roots, you'll be able to work your way through all of this. And you'll remember it for when you have to take your SATs or when you go to college biology, because you'll remember the word roots and how to work your way through it. That's what I want you to be able to do, okay? I don't want you to memorize it and forget it in 2 weeks. I want you to get the word roots and get the concepts, and then that way you should be able to work your way through it, okay? All right, so let's go to chemical change. So we've done physical changes, right? Now we're looking at chemical changes. And it gives us here, I need one of these that rolls, don't I? Okay, it gives us here the combustion of methane. So we have CH4 plus O2 yields CO2 plus H2O. Okay. Now, what does this actually represent? And I'm going to show you. This represents a methane molecule. That's a carbon with 4 hydrogens attached. This represents an oxygen molecule. It says that it produces carbon dioxide plus water. That's what that chemical equation actually says. The left-hand side of the equation are the reactants. You have to know this. The right-hand side are the products. Well, that makes sense because the reactants react together to yield the products. And the arrow is red, yields or produces. You can read it either way. Just like when you read an equal sign, you say equals or is, right? This is yields or produces. So anything on the left side of the arrow are the reactants because they're going to react together. And they're going to produce the products. Everybody over here are the products. So far, so good. Remember, there's 1 carbon because there's the invisible 1. There's 4 hydrogens. There's 2 oxygens. There's 1 carbon with 2 oxygens. And there's 2 hydrogens attached to an oxygen. That's what those subscripts mean, correct? Now, this is not a balanced chemical equation. And the reason I say that is matter is neither created nor destroyed. It can only change forms. And you don't have to remember all this, but I'm going to tell you the truth. Well, that means that I have 4 hydrogens over here. Where did the other 2 go? They disappeared. Do you see this? So this doesn't work. And I have 2 oxygens here, but I have 3 over here. Where did that come from? So you have to do something called balancing a chemical equation. And you notice they went back in, and I'm even going to use a different marker color. What they did was they went ahead, and I want you to notice they put a 2 in front of this guy, and they put a 2 in front of this guy. Now notice they had water first and then carbon dioxide. And those of you that have already had algebra, the commutative property applies. These can go on either side this way. These can go either way this way. Doesn't matter there. Okay? All right. But you notice they put a 2 there. What does that 2 represent? The 2, which is the coefficient here, tells me that there are 2 oxygen molecules. The 2 here tells me there are 2 water molecules. Does everybody see what the coefficient means? It tells you how many of those molecules are actually there. So you're not allowed to change these little subscripts, but we can change how many molecules of each thing are there. Now I have 1 carbon on either side. I have 4 hydrogens on either side. I have 1, 2, 3, 4 oxygens, and 1, 2, 3, 4 oxygens. And now matter is neither created nor destroyed. It can only change form. It's going from one side to the other. We're good. So far, so good. So this is a balanced chemical equation. Reactants on the left, products on the right. The subscripts represent how many atoms are in the molecule. The coefficients represent how many molecules are actually in the reaction. Now, how he's going to ask this is this. Look on page 140. 511. It says one of the main chemical reactions used to run an automobile engine is the combustion of octane. That's the burning of octane, C8H18. And he gives you there the equation for the combustion, the balanced chemical equation for the combustion of octane. A, write the chemical formulas of the reactants in this equation. All right, you guys tell me, what are the reactants in this equation? Go ahead, give it to me. Good.
And 25 of it.
Thank you. Those are the reactants. How do I know? They're on the left-hand side of the arrow. They're reacting together. Okay, then it says, give me the chemical formulas for the products. Go ahead, Jacob, what are they?
It is 16 CO2
Okay,
and 18 H2O.
very good. Okay, reactants, products, right? Thank you, sir. Then C says, how many molecules of octane are used in this reaction? How many molecules of octane are used in this reaction? 2. Then it says, how many molecules of water are made in this reaction? 18. Does everybody see how that works? Because he's going to ask you questions like this on your test. Okay, then on page 140 we get to photosynthesis. And you're going to have to memorize the equation for photosynthesis. So let me tell you the easy way to memorize it. You ready? Okay. What do plants suck up in their roots? Water. And what do plants inhale? We inhale oxygen. What do plants inhale? Carbon dioxide. And what do plants like when the sun comes up? Sunshine. Sunshine. Right? Okay. And what do plants exhale that we're happy about? Oxygen. And the reason plants go through photosynthesis is to produce glucose, which this one you have to memorize, C6H12O6. Now I want you to notice glucose is the healthy sugar that our bodies use on a cellular level to burn. And it is a carbohydrate. I want you to notice if you divide the whole thing through by 6, you get a carbon attached to a water. Carbohydrates are carbons attached to water, or really it's water is attached to carbons, but that's okay. And glucose is a carbohydrate, C6H12O6. Okay? Now, this is not a balanced chemical equation. And so how I teach this in biology, because I don't want to teach you how to balance equations, you don't need to do that. So you write this out because you go, plants inhale carbon dioxide, they suck up water, they love sunshine, they exhale oxygen, and they're doing all this to produce glucose. You have to memorize that guy, and then give everybody a 6 that doesn't have one. You're done. Now it's balanced. He's got a 6. He's got a few of them, right? That's the balanced chemical formula. But I want you to think your way through it. You should be able to think your way through this. Plants, and then glucose. Right? Give everybody a 6 that doesn't have one. Okay, so far so good. Now this is how plants photosynthesize. This is a very huge oversimplification. But this is the summary statement for photosynthesis. It requires energy. And we're told in the text that even with the sun's energy, it's really not enough energy for the plant to make enough glucose to survive with photosynthesis as it runs just the normal way. There are 2 ways to speed up a chemical reaction. You can heat up the chemical reaction because when you heat it up, the molecules are moving more quickly. And what happens is to get a chemical reaction, you have to have the molecules colliding with each other. So when you speed them up with heat, they collide more frequently, and therefore you have a faster chemical reaction. So far, so good? Can't do that with a plant, though, or it ends up being dinner. You know, it dies. You can't just speed it up, heat it up. So God put in it what are called catalysts. And actually, catalysts in living systems are called enzymes. The catalyst's job is to speed a chemical reaction without being used up. So you can kind of think of them as going like this. They're making it go faster, but they're not getting used up. They're just doing the job, doing the job. That's their job. And this is actually part of the reason why, health-wise, we should eat raw fruits and vegetables as much as possible. Because when you cook them, you destroy the enzymes in them. And we benefit from eating those enzymes. So if you're going to eat pineapple, don't eat canned pineapple. Eat raw pineapple. If you're going to eat, eat an apple, don't eat cooked apples. The point is that the raw food still has the enzymes in it, so you want to eat those. And those enzymes are catalysts that actually help us in our cellular processes as well. God meant for us to eat a lot of raw food. Yes?
Just a note about catalyst. It doesn't necessarily say that it says that it alters the speed.
Yes, because some catalysts actually do slow things down. But in general, the vast majority of the time, catalysts will, and it's interesting because in the chemistry book, it actually says it speeds the reaction. And here it just says it alters the rate of reaction. And I agree. When I was in school, I learned that it altered the rate of the reaction. But the vast majority of them speed it up. Okay? And in the case of photosynthesis, who remembers what the catalyst is in the plant? No, somebody other than you. And I'm glad you're ready, but come on, somebody else. Come on, Emily, you going to tell me? Do you remember? No? Somebody said it? Thank you. Chlorophyll. Catherine said chlorophyll. Chlorophyll is the green pigment that we see in plants, and that's why they look green. Chlorophyll is the enzyme, the catalyst, that is used to actually speed the photosynthetic process so that the plant can make sugar fast enough to survive. Okay, it needs more than just sunshine to survive, doesn't it? It needs all of these things in place. We've really got to go. Listen, this next week, it's going to look overwhelming. It's not overwhelming. I'm going to walk you through it. It's going to be fine. Okay? We're going to have some fun with it. Yeah. All right? Have a good week.